Okay, we're going to get started, and we're basically going to pick up from where we left off last time. I think I'm only missing one person that hasn't gotten their exam back yet, and that's Mr. Aldaz. Does anybody know Jason?
Oh, yeah.
He wasn't here on Monday, and he's not here yet. Okay, Aldaz. Does anybody know him?
No, but I don't recognize him.
Okay. We're getting back to the frequency response, which is what we were doing last time. Last time we basically established, which wasn't too difficult, this result right here, which says that when we drive an input with a complex sinusoid, which happened to have been at a frequency omega naught hat, a magnitude of A, and a phase of phi, we got, as the output, we got that exact same input plus a complex weight applied to it, which is defined as the frequency response. And it's this equation right here, which is how we calculate the frequency response given the coefficients. You guys talking about something that I should know about? No? Okay. So now we're going to move on from there, and we're going to develop an extremely important result, and we're going to take advantage of superposition in the fact that when we have a linear time invariant system, we can apply two different inputs independently and form the composite output as if they were superimposed all at once. Remember how linearity works? You can apply the individual input number one, get the response, apply input number two, get the response, and then combine those output responses, and we know if the system is linear, that's equivalent to having applied the two inputs simultaneously. So how we're going to take advantage of that is we want to consider a real sinusoid, a single real sinusoid, and we haven't developed the frequency response result for that yet. We only have it for the single complex sinusoid. But now is when we use the power of all the math that we've been learning throughout the semester, namely Euler's formulas in this case. We expand out that cosine into two complex sinusoids. So one is at the plus frequency, and the other one's at the minus frequency. And we know from our frequency response analysis and definitions from Monday that the individual responses to each of those complex sinusoids can be obtained just by saying, if this is the input, magnitude and phase, it comes through to the output at the same magnitude, with the same phase and the same frequency, but then it's also picking up the frequency response at that frequency omega naught hat. That makes sense? Remember, a sinusoid goes in. This is a fundamental concept for all electrical engineers, in my opinion, whether it's discrete time or continuous time. A sinusoid goes into a linear time invariant system, and it comes back out again just as it went in, as the blue underlined pieces of the equation show, plus there's an additional term that's been added or product into this, and that's the frequency response at that frequency. So it picks up the gain and the phase of that associated with h of e to the j omega, which is the gain, amplitude response, and the phase shift that the system imparts to that signal. Does that sound reasonable? We send a signal through a filter, and it comes out of that filter in general, and it comes out at a new magnitude, and it comes out having picked up a phase shift, and that's because h of e to the j omega naught is a complex number. So it says at that frequency omega naught hat, we pick up through that function a magnitude and a phase. Likewise, the negative frequency signal, which has an amplitude of a over 2 and a phase of minus phi, because of the minus sign out in front, it comes out of the system with the minus phi and the a over 2 amplitude and at the negative frequency, and it is picking up the frequency response of the system at the minus j omega naught hat value, which again is some complex number, magnitude, and phase. If we had to stop here, the result wouldn't be quite so beautiful, but fortunately, we can simplify this. We can simplify down the result of applying this input into a nice compact form at the output. And this is the result that's on the next page, but this is the result that I contend that all electrical engineers need to know, whether it's continuous time or discrete time. The way we're going to simplify the result is we're going to assume that the FIR filter has real coefficients. And we're going to prove a little bit later today that if it does have real coefficients, the frequency response is conjugate symmetric. And conjugate symmetry just means if we go to plug in the negative frequency, h at e to the minus j omega hat as opposed to e to the plus j omega hat, we get the same frequency response that we'd get at the positive frequency, except now we have to conjugate the answer. So that's what's meant by conjugate symmetry. And the symmetry idea is if we think of the frequency axis here, that's omega hat, so we think, well, let's do it like this. That's omega hat, and over here we have minus omega hat and 0. So what we're saying is if we consider the frequency response at this point versus this point over here with respect to varying frequency omega, we have the conjugate at the minus omega frequency relative to the result at the plus omega frequency. So that's the conjugate symmetry. And what does conjugate symmetry amount to? It says that in this case, the magnitude response is identical to what it would be at the positive frequency. It's just that the angle is the negative of what it would be at the positive frequency. So the magnitude response is identical. The phase is the negative. That's the conjugate symmetry. You're going to see that. Remember the GUI that I had up on Monday, the one that you're going to use in the lab on Friday? That displays that beautifully. Question?
So if we were to plot the phase, then the negative, it would be just underneath.
He would be the opposite. Yeah, let me draw a little picture here of the whole deal. So if this is the magnitude up here, and this is the angle down here, the angle response would be, or the magnitude response of a filter, suppose it's a low-pass filter, it might do something like this. It's going to be symmetrical, although I didn't quite draw it perfectly. It should fold right about this location. So whatever we see on the positive frequency side is the same on the negative. The phase, on the other hand, if the phase was doing something like this on the positive frequency side, it should fold but then flip, or mirror, I mean, so it's going to be like that. So those 2 points are the same, and this point is equal and opposite to the point on the negative side. This shows up over and over again in continuous time and discrete time signals and systems, this symmetry idea, or conjugate symmetry. So I'm wanting to invoke that property, saying we have real coefficients in our filter. Now in modern digital signal processing applications, filter coefficients are not always real. The types of things I deal with in some of my graduate classes and research and consulting work, they may in general be complex. then this property doesn't hold, and then we have a different scenario on our hands. But very, very frequently it does hold, that they are real coefficients and the symmetry property holds. There's other properties that hold even if it's not symmetric, I mean, even if you don't have real coefficients, but the most simplified form is what we have here. And in terms of the continuous time domain, which you'll start studying next semester in 2205, the real coefficients do hold because we use elements R, L, and C values in an analog circuit that end up corresponding to filter coefficients that are purely real, I mean, in the sense of the differential equation that would result. And some of you are taking differential equations now, some of you will get to it later, but that's one of the reasons why we can do discrete time domain and not have to be so concerned about the solving business, because the difference equations are easier to solve and work with than the differential equations are. But there is a direct analogy to the FIR filter coefficients and lumped element circuits, let's say. So we use that conjugate symmetry result right here. We started off, let's get rid of all this trashy stuff, if I can get it right. It's stalling on me for the moment. Nope. Here we go. That's the term we were trying to manage to simplify this result in equation 6-9. So we're going to use this identity right here to make that substitution. We're going to replace h of e to the minus j omega hat by h conjugate of e to the plus j omega, and that goes on right here. So there it is, dropped into there. But this thing now breaks itself out into e to the j omega naught hat, and then we have a minus angle h of e to the j omega naught hat. So we have this minus sign hanging out in there because of the conjugation. Does everybody understand basic conjugation? Remember first week of school when we went through conjugation of complex numbers? Just change the sign in the imaginary part, but what does that do to the angle? Well, the angle is ordinarily the arctangent of y over x, so now it's the arctangent of minus y over x, so it flips the sign. Or the other way of getting at it, if this was r e to the j theta, then when we conjugate that, the conjugation operation goes hunting for the j values or the imaginary values, and the conjugation means flipping the sign on the imaginary part. So that means the angle is now the negative of the previous one. So I stopped there for a second based on the dull stares I was getting, like, what are you talking about? I just hopefully refreshed your memory. So the minus sign is now on the angle. The big deal is that now I can do some combining. The a over 2, which is sitting out in front of both of these terms, can be brought down as an a outside of the entire term, and the 2 can be brought up inside the square brackets here. And then what I'm going to do is I'm going to take and expand h out into its polar representation, which means I have the magnitude. And because the magnitudes are the same here and here, I can pull that out front. And then the angle associated with h of e to the j omega is either the positive value or the negative value. So with the first term, I have the plus sign on here. And in the second term, where I have the minus sign out front already for the negative frequency, which is this piece in here, I now need to deal with the angle associated with H conjugate, and that's the minus sign. So I get to have a minus and a plus on the inside, so I net out a negative angle. And the beauty of all of this now is that I can now go through inverse Eulers and collapse that right back down into a cosine. So I've got the signal coming out with an amplitude A. It went in with an amplitude A, and it comes out picking up the magnitude response of the filter at omega naught. It has the original phase of the cosine, and of course its frequency, and then it gets phase shifted by the phase shift that the system applies. I have that in a blue box because I find as I move on from here, I'm constantly going back to this, or people come in for office hours, or some discussion ensues, and this becomes a necessary thing to keep reminding people of. So if I wanted to make a picture of what we're seeing here, I'd have a block diagram, and I'd say we have our linear time invariant system, which is our filter. So we put in over here A cosine omega naught hat n plus phi. That's the x of n. And what comes out over here for y of n is what's in the blue box. And of course the assumption here is that this is in steady state, so we have that cosine signal present for a very long time, essentially. So if we were looking at the continuous time version of this up in the lab with a proto board and some analog components, we could have something simple in our circuit. Suppose it's a resistor in series and a capacitor in shunt, and we have X of t and Y of t like that. We would see this exact same behavior. I could take the oscilloscope and I could probe and see the waveform at the input, and then I could put another probe on the waveform at the output, and I would see that the waveform at the output would be of the same frequency as the waveform at the input, except it would have a different amplitude by virtue of that factor right there, scaling the amplitude. And then it would pick up a phase shift by virtue of the system imparting an additional phase inside the argument of the cosine. And if I was to change the frequency up and down, as if I was moving it by turning a knob on a function generator in the lab, which produces the sinusoidal output, I would see that it would change, the relative amplitude and phase shifts would change from input to output depending upon what frequency I'm at, because I'm exciting the circuit with a different frequency, and it's got a frequency response which is not constant with frequency. Like I said, all EEs, computer engineers, need to know that, because that's just a fundamental concept. And we're getting at the heart of the matter, how to actually calculate what goes on by using the frequency response. That tells us exactly how much amplitude scale change happens from input to output, and then the angle associated with h of e to the j omega naught hat tells us how much phase shift occurs as I move it. And of course what's critical here is that it's not just omega hat, it's omega naught hat. That's the specific frequency that our real sinusoid is going into the system at. We're going to go through some examples here shortly. A generalization of this result is to say, and this is like the super version of what's on the top of this page, is if we put in a sum of sinusoids, possibly a DC component, and a bunch of sinusoids all with different magnitudes and phases and different frequencies, then the output will be the input DC value picking up the DC gain of the system. In other words, we take the frequency response and insert omega equals 0, and that gives us the DC gain of the filter. That's how much the output DC term changes by. and then each of the individual sinusoid terms pick up the magnitude response at that respective frequency, omega hat k, and they pick up the phase response at that particular frequency, omega hat k. It's simple, isn't it? I mean, it's just a collection of sinusoids go in, the system acts on each individual sinusoid using superposition or the linearity, and each individually get imparted to them the magnitude and phase response of the system at those individual frequencies. And of course, that's what the idea of a filter would be, is we would want some frequencies to pick up a nice healthy gain and other frequencies that contained in the signal to get essentially no gain, so that our filter acts as a filter. I mean, it passes some signals and removes other signals. So let's take a good example of that I put together here. Suppose the FIR filter has three coefficients, 1, -1, and 1, and the input is composed of a DC term, a discrete sinusoid at pi over 4 radians per sample, and a discrete sinusoid at pi over 3 radians per sample. So the first step is to go ahead and get the frequency response in general terms, in terms of just omega hat. Remember how we do that? We just have to evaluate, the formula says, it's going to be the BK coefficients times e to the minus j omega hat n k, omega hat, let's do it like this, b sub n omega hat n, so we just plug in the individual values. We have 1 on the DC term, so that comes out as 1. We have -1 on the first coefficient when n is equal to 1, and then +1 on the third term. So that gives us those three pieces to the frequency response. Make sense? You might notice, and some of you do eventually notice this from my past experience in teaching the class, is that it looks like the frequency response is just superimposing a signal that's picking up a 0 sample delay, a 1 sample delay, and a 2 sample delay. In other words, that e to the j factor is just due to time delaying the signal through the filter by the respective number of samples. And that's correct. The next step that we could do, if we wanted to, and last time we talked about this some, the form that's shown right up above here is adequate to go into MATLAB for actually plotting the frequency response or entering into your calculator, and we'll work through the example sheet here next. But if you wanted to get some additional insight, it's sometimes useful to do some factoring on this in order to see more about what's going on under certain circumstances. So in this case, I went in and factored out an e to the minus j omega from the entire frequency response. And that was done in combination with Euler's identity. So if I factor out e to the minus j omega hat, that means on the first term I have to put back in an e to the plus j omega hat, so it nets out to the 1. Then the center term will be a -1, since that factor is already present in what I pulled out to the left side. And then the end term has to be just 1 e to the minus j omega hat. And then notice what I can do is I can take these, the first and the last terms can be formed up together to form a cosine. See how that works? Just for added understanding, suppose this was a minus sign in here, then this would have been a minus sign over here, then what would have formed? A sine, right? Except we would have had a j hanging out in there, which would have been a little bit ugly, but it would have happened. And there's another example on that here that's coming up shortly. So the added insight we get from this is we can make some observation, in particular, like when we see this term inside the square brackets, we can observe that there is going to be some frequency where we'll annihilate the input, because for some value of omega hat, wouldn't you agree that 2 cosine omega hat will be equal to -1 at some point? Because omega hat's going to run from 0 to 2 pi. So there's going to be some value where inside the square brackets we have 0. And as a matter of fact, it happens for one of our input frequencies. We're putting in a DC. What's the DC gain of this filter? Well, the DC gain, putting in omega hat equals 0, is just unity, so that's okay. A trick on how to get the DC gain is to just add up those 3 values, and that gives us the DC gain, which is going to be 1. How do I know that works? I'm kind of going off and picking up a few little odds and ends. Well, the DC gain is always just going to be the sum of the filter coefficients, because if we were to go over to here and set omega hat equal to 0, e to the j 0 anything is always 1, right? So that means we'll just pick up the filter coefficient, the sum of the filter coefficients. We also have a sinusoid at pi over 4, so we evaluate the frequency response at pi over 4, and that doesn't work out quite so beautiful, but it does work out to be a number we can at least put into our equation. So we have 0.4142 for the magnitude response at pi over 4, and then we have an angle phase shift of minus pi over 4. Then we also have a sinusoid at pi over 3 going into the system. So we evaluate the frequency response at that location, and we see from the math that that is where the annihilation occurs. -1 plus 2 cosine of pi over 3 is exactly 0. Gone, annihilated, whatever term you want to use. So it comes through to the output, because again, we get the output by, we get down here by multiplying each of the respective terms by the magnitude response, and then apply the phase shift inside the argument of the cosine. So the DC term picks up the gain of 1, which makes it come out as 10. The pi over 4 radians per sample cosine wave picks up the gain factor of 0.4142 times the magnitude of the input, which was 4, and then the phase shift, the minus pi over 4, gets incorporated inside the argument of the cosine as an additional phase shift due to the filter. So we get 2 terms coming at the output. So we've removed one of the input signals and we've modified the amplitude of the other one. We've reduced it down slightly. And I plotted it, plot the magnitude response and plot the phase response on the interval. This is omega hat. Interval 0 to pi. So you can see exactly where the pi over 4 frequency is picking up the magnitude of 0.4142 and the phase shift of minus pi over 4. And the sinusoid that comes in at pi over 3 radians per sample happens to hit that annihilation frequency dead on, and it gets excised, or like I said, annihilated. You can see that if we're either side of that pi over 3, we're not going to have that annihilation property, but it depends on what you're after. If you're after just annihilating a single frequency, then this technique would work. Can anybody think of where annihilating a single frequency might be valuable in a practical application? Either be a military application, audio signal processing, okay, jammers. So the military are our enemies, and we use them on our enemies. They use them on us. One form of jamming is called tone jamming. It's not at an audible tone, it's at a microwave or RF frequency, but it's just simply to broadcast a pure tone and just throw it up there in the face of the enemy's receiver so that it kind of gets saturated with that pure tone. And the idea is to put that tone in the bandwidth of the receiver front end so it kind of makes it go crazy. It can't handle all that tone jamming. But if you could put a filter at the front of the receiver that would annihilate just that one single frequency, you'd still have hopes then of getting something reasonable recovered, because your information probably spans a whole band of frequencies, and if you have to annihilate a jammer right in the middle of that, you'll take out a little bit of your signal, but not a whole lot of it. Now you can imagine that most jammers don't sit still, they move around. So then how do you deal with that? We haven't talked about that, but what would your imagination say you should do? So you can do spatial filtering with multiple antennas. You can null out jammers that way too. We're talking about what's called temporal or time domain filtering, but the comment about having multiple antennas, you can do the same thing with multiple sensors or antennas, and you can form a spatial filter so that in a certain direction you don't let the jammer in. I worked on a system like that that was going on the nose cone of a cruise missile, and it was an adaptive filter so that as the missile was flying, this was during Desert Storm, if you remember, that was the first application of smart bombs, and they were targeting certain locations, but they were using GPS, and GPS is not jam resistant entirely, so plus an inertial navigation system was on board, so they fused data from those two systems to stay on target. But the idea was to have an adaptive antenna array that could steer a null in the direction of a jammer, which might be a high power source on the ground trying to confuse the smart bomb as to where it's going to go. You adaptively have to steer the beam because as it's in flight, the angle that you want to take the jammer out at is going to be changing. But another really simple example of where it might be useful would be a single tone could be excised. A lot of times in audio processing, we get interference from the lights and basically the power line frequency. The power company generates our AC power at 60 cycles per second. So you all know what a 60 cycle hum or buzz sounds like. You've probably heard a PA system where you have that humming sound in the background and it's quite annoying. That stays pretty stationary, so you could notch that out, and if you're not caring about bass notes from bass instruments right at 60 hertz, maybe you're okay. If the bass guitar hits something right at 60 hertz, well, we won't hear it because it gets removed. But in most applications, it could be in a PA system or something. And then other frequencies of interest might be 120 hertz because a lot of times the second harmonic shows up too. If we have a 60 hertz signal present and we have some nonlinearity or some other processing going on in the electronics, it's very easy to get the second harmonic, which would be the 120 hertz. So you might have to deal with that too. Any questions? Is this interesting or it just doesn't seem very exciting? It's signals and systems, and it's, if you're the man or the woman called on the scene to fix the problem, you might be designing a filter and understanding what you need to do to fix or eliminate some problems by filtering. Okay, what about the transient response? We're going to, let's do the worksheet before we go do that. Does anybody need a copy? I've got 2 copies left. They're sitting right up here. So Kevin, maybe you can grab both of them if anybody else needs one. So here we're given an LTI system that has this impulse response. So the first thing is finding the frequency response. So let's just take a few minutes and have you try to get the frequency response from that impulse response. And again, you're going to be using, remember the definition, h of e to the j omega is the sum from n is equal to 0 to m of bn times e to the minus j omega hat n. And if you're rushing along and already have the answer, which I'm suspecting several of you do, go ahead and simplify it while you're at it, or do that trig simplification that I've done in a couple of the examples. And I'm not going to pause the recording because this is going to happen really fast, right? In terms of getting the answer. But since there's a lot of people that aren't here today, they're probably going to be wondering, what is everybody doing? I guess if it was the TV show Jeopardy, that clock ticking sound is played in the background, right? Or some other game show. Which reminds me, I don't watch TV that much, but my wife does. A month or so ago, there was a Jeopardy show on that had a computer playing against contestants. I don't know if anybody saw the articles on that, because I think it was written up in the IEEE Spectrum, too. Yeah. Okay, is anybody ready? Like, how about somebody up in the upper left corner? Anybody up there want to tell me what you got for the frequency response? Not simplified, just in raw form. You don't have it? No term? You have it? Okay. Yep. Okay, how did you get that? Did somebody want to explain how you get that answer? Because I'm sure somebody else has got that same answer. What was the technique? Jeff, you always answer questions. I know you
pull 1, 3, 1 off of the impulse.
Okay.
And then the way I set up the summation or whatever is from k equals 0 to k equals 2.
Okay.
So then you just kind of stick it into the terms. So the BC value is going to be the first b sub k, which is 1, and then just keep adding on e to the negative j omega hats.
For each of those, yeah. Effectively, right? Mm-hmm. So you could think of this as being a minus 0 stuck in there, which means it's just plain 1. I could say piece of cake, but maybe you don't like eating cake, so I don't know. Pretty straightforward, though. So how about simplifying? Did anybody get this to the simplification step? No? You just answered, but does anybody else have it? The trig part? Because it'll be helpful in answering that third bullet right there. Because right now, if you have to try to answer the third bullet, you'd look at those three and say, I don't know, is it possible that as omega varies from 0 to pi that I get 0 at some point? But if you do this factoring, you can see it more clearly. Anybody want to take a shot? Okay, we'll take Jeff's answer.
E to the negative j omega hat. Or do you want me to do the intermediate step, or just want to give you the answer?
You can just give me the answer.
I got 2 cosine omega hat plus 3.
Now the question is, how did he get that?
I factored out an e to the negative j omega hat.
Okay.
Yeah.
Then you had from the first term down here, if you
E j to the omega hat plus 3 plus e to the negative j omega hat. At first I did pull out the e to the negative j 2 omega hat, but then I realized that it wouldn't really simplify if you do that. So.
Okay. The trick is trying to get 2 equal and opposite signed complex exponentials. So an e to the plus j and e to the minus j, because we know those can be stuck together to form a cosine. And so because you'd have to put a 2 inside of each of these to make them into a cosine, we have to put a 2 on the top to balance that off, and that's how the 2 gets pulled out in front. So then we're left, in the factoring, we're left basically with that stuff that I just circled in green forms the cosine. And now we can go on and see what bullet number 3 is, because if we take and think about what we have from the simplification, what it comes down to is, does that quantity, 2 cosine omega hat plus 3, ever go to 0 as omega sweeps between 0 and pi? And as omega sweeps between 0 and pi, what's the cosine going to do? It's going to take on values between 1 down to 0, right? 1 to minus 1. So it'll start off at 1, and then when the angle goes up to 90 degrees or pi over 2, it hits 0, and then as it swings over to the other side, we get minus 1. But plus and minus 2 can never, those are the extremes of the swing, and they can never combine with the plus 3 to go to 0. Does that make sense? This third bullet, though, definitely can get more complicated than this, and it's not too hard for it to get complicated enough that you can't answer this question without using more powerful tools like MATLAB's frequency response tools, or something that solves the roots of a polynomial. That's something else we'll be getting into, is using polynomial rooting functions in MATLAB. Question?
So to solve that, it's just basically solved by inspection, or
solved by inspection.
Throughout, you plug in every value between 0 and 5.
You'd sweep it, and then you'd see, does it ever go to 0?
It would be a pain in the butt.
Exactly. What we'll see later, though, and we're going to be getting into this in the next chapter, what this actually leads into is finding the roots of a polynomial, and what will be the polynomial that will be rooting. First, I'll write out what the answer is here. 2 cosine omega naught hat plus 3 does not equal 0. In general, we're going to be having to root polynomials, and maybe that term sounds kind of weird to you. I don't know. It's probably slang to say it that way. Find the roots of a polynomial. So the polynomial that we'll be rooting will be something like 1 plus 3 z to the minus 1 plus z to the minus 2. I'm just replacing the e to the minus j omegas by a quantity z, and we'll be wanting to find when that is equal to 0. Or equivalently, if we multiply this out, we'd have z squared plus 3z plus 1 equals 0 if I just multiplied left and right sides by z squared. And you know how to root a quadratic, right? There's something called the quadratic formula to do that. But when we have to go to higher degree polynomials, then we rely on some numerical algorithms. And MATLAB has a function that does that. The roots function finds the roots of polynomials. We haven't had to use that yet, but we will be using that. Okay, what about the last question? What is the frequency response at a particular frequency, namely pi over 4? So to do that one, we just need to plug in that frequency. So if we started off with the original form, it'd be 1 plus 3 e to the minus j pi over 4 plus e to the minus j 2 times pi over 4. And now we have to pull out our calculator or do some trig stuff as a side calculation. So this requires some more detailed work. I'll have a solution sheet up that shows the expansion on this, but those of you that have the calculators that can handle this, you can just punch the numbers in. Otherwise, you can break it up into rectangular form. Now, for example, the real part is going to be something along the lines of 1 plus 3 cosine of minus pi over 4, and then the last term brings in a cosine of minus pi over 2. And then for the imaginary part, 3 sine of minus pi over 4. I'm just using Euler's identity now, plus sine of minus pi over 2. And that would give you the real and imaginary parts, but most of the time we'd want this back in polar form again. So we'd want to flip it back to the polar form. And again, you see this is kind of like the complex or the phasor addition formula, just another application of adding up complex numbers that we started off in the first chapter with.
Did you just stick that into the trig or the trig simplification that we found?
Oh, definitely. Yep. It just depends on the form, though. If you were to go that route, then you still are going to have this e to the minus j pi over 4 sitting out in front, and then you'll have the 2 cosine.
You have to convert one to the other.
Yeah, you've got some things to deal with.
Well, that just ends up being square root of 2 plus 3 times e to the negative j pi over 4, which would be polar form. So. That's
right. So you brought up the good point that this will be the magnitude right there, and then there's the angle. So that, in this case, that works out very nicely. Any questions? This is the type of thing that we'll have on the quiz on Friday, just to be practicing at this, and you'll be dealing with these types of observations in the lab on Friday as well. If you're expecting there to be more, there isn't more to that particular type of problem. That's pretty much all there is. But now we're going to do more. Yeah, we're going to do more beyond that, but for that part, that's all there is. Okay, one little topic that we haven't spent any time on yet, but I hinted at we would get to, and that's steady state and transient response. right now we've been formulating all of this under the assumption that the input runs from minus to plus infinity. As a practical matter, we never start at minus infinity. We approximate starting at minus infinity. Basically, we just start far enough back in time, or the other way around is we start when we flip the switch on the piece of equipment and we start generating a signal that goes into our system, and then we wait a certain amount of time to say the system is now in steady state. That's the more typical. So how long does it take for the output to get in steady state when the input is just turned on? So we model that mathematically by putting this u of n on our complex sinusoid. Remember, the unit step function is something that is 0 for n less than 0 and then is a 1 when n is greater than 0 or greater than or equal to 0. So it's a gating function, and it's just a way of modeling flipping the switch on our signal. So our complex sinusoid is being generated and it's being gated on with the unit step function. So we can take that into the FIR filter equation, and so this becomes the composite x of n minus k inside the convolution sum formula. And when we take the unit step function in particular and write it as u of n minus k, remember on the k-axis, so what would u of minus k be? It would be the step function that instead of turning on at n is equal to 0, it turns off at n is equal to 0 because we just spin it around on the axes. And then if we let it be n minus k rather than just minus k, we get a step function that is basically a reverse step function that turns off. It comes up from minus infinity and shuts itself off for k greater than or equal to n. And of course, this whole thing slides over depending upon the value of n that we're evaluating our expression at. So the net effect of that is, when we combine that with the complex sinusoid right here, it means that when n is less than 0, there's no overlap in our convolution sum. So in our table entry method, we'd have no terms to multiply and sum up. When n is greater than 0, we're going to have a few terms that are sitting in here. Like that, that'll overlap. And then we can carry this all the way through to when n is greater than or equal to m, we have full overlap. And then from thence on, we're just entirely, completely engaged the filter's impulse response. So that gives us three terms, or three forms of the output. For n is less than 0, nothing comes out of the filter because nothing has arrived at the input. For n between 0 and just less than m, we have a partial output where we're only engaging coefficients of the filter from 0 up to little n. And then when n is greater than or equal to m, we're in the full steady state scenario where we're fully engaging all the coefficients of the filter. So we have a short little interval where we only have part of the filter's coefficients engaged, and that's what's called the transient response. So by having the input turn on at n is equal to 0, we're not really that far different from the input starting at minus infinity. We just have to wait for m samples to go by, and then the output will be fully steady state. And we'll go back to the same example we were looking at earlier where the filter coefficients were 1, -1, and 1. Put in those exact three sinusoidal signals, and I'm doing this all in MATLAB notation. So here's the DC, here's the first cosine, here's the second cosine, and I'm using a little support function. I've got the time axis set to run from -5 to 20 samples, and I will gate that signal with this little support function, which is defined on the next page, which just models the step function. And then I run it through MATLAB's filter function, where I use the coefficients of the filter, just like we've used in filtering before, put in x and look at y coming out, and I do a subplot, so I have the input over the output. So the input's gated on, and the reason why I started at -5 was just to get more of a picture so I could back up and say there's nothing happening from -5 up to 0. I just wanted to put it in the plot so that it would be more believable that something mysterious wasn't going on there. So there's nothing at the input to the filter until effectively n is equal to 0, at which time the filter begins to send out an output. So the first sample that pops out of the filter is right here. The next one is a negative sample and then a positive. And that's 3 samples now that have gone through the filter. So now the transient interval is ended, and from thence on the filter is in steady state. And we know from our earlier analysis what happened when we sent the 3 signals through this filter. The DC came through as DC of 10. The second sinusoid came through but at a reduced amplitude. And the third signal, which was also a sinusoid, what happened to it? It was annihilated, right? It was gone. So looking at that steady state output on that bottom plot, what does that look like we have? Just visualizing, what do you see? What does it appear? Pardon me? It's a single sinusoid, but we also have a DC present, and what did the DC do? It just raised the signal up onto an offset of 10. So the impact of the DC is to just make the signal be riding on a bias or an offset of 10, but then it looks like just a single sinusoid is the only time-varying portion. You will relate to these things really well once you start playing with the test equipment in the lab, because the function generator has a knob on it called DC offset. You can look at the sinusoid coming out of it on the oscilloscope, and if you twist the offset knob, you'll see the waveform on the scope will ride up and down with the DC offset. For this class, we have to be content with plots in MATLAB, which are our believability factor. That's what the computer is generating, and that's what's really going on. The definition of the step function is in here, and I'm not really going to drill down on it. I will say, though, that a time is coming, I think maybe even in this lab, if not, it's the last lab where you're going to get introduced to the find function. Has anybody?
It's lab 8.
Okay, it is lab 8. So has anybody played with the find function yet? Okay. It's a very cool function. It saves you a lot of time. It allows you to write faster code, because MATLAB's a vectorizing language. So the find function, what it does is you put a logical statement inside there. So here n is a vector. It's a bunch of time samples. And it's what you're telling MATLAB to do is find within that vector where the values held in that vector are greater than or equal to, or whatever the logical statement you want to put in here. Or you can and or a bunch of statements together. In this case, it was just where it's greater than or equal to n naught. And then what the find function kicks out are the indices where that condition is true. And although this is not something you can do in C or Java, unless you use operator overloading or something like that in a class, you can do something. You can put something in the left-hand side with the find function. Normally, you think of putting indices in the right-hand side in MATLAB, but you never do anything on the left-hand side. But what you can do with the find function is I can say, I can put the indices on the right-hand side. Well, I can put a collection of values on the right-hand side, and then I can say I want to poke those values in to some vector, x in this case, at the indices that were that were returned by the find function. So you're putting something on both the left side and the right side. So it's kind of a neat trick. So if the vector x, let's say, was this big long vector that has all these slots in it, and the find function returned, let's see, pick the right, returned indices to this slot, maybe this slot and this slot, returned the indices to those three slots. So I'm sitting over here with another vector, say y, that contains 1, 2, 3. So if I put y on the left side and I put x on the right side, or y on the right side and x on the left side, and I put a vector containing those three indices inside of it, which would be, in this case, a vector that contains, say, 1, suppose this is 1, 10, 11. What MATLAB is going to do is it's going to go throw 1 up here in that first index location, 2 is going to get pushed onto there, and 3 is going to get pushed onto there. Everything else in the vector x gets left alone. So you can do some neat things. What it mostly saves you is the need to have to set up a for loop. Ordinarily in a programming language, you'd say, if I want to modify the contents of certain elements in an array, I would just set up a for loop, and I would just scan down through the array, and I would have if, then, else, or case statements that would select when some condition occurs, and then I would set a value, poke a value in. This way I can just bang it out just with one command like that. Once you learn how it works and you see the beauty of it, you'll say, how could I ever live without this? But you'll have to return back to C or something, and you'll say, I will have to live without it. But while you can get away with it to make MATLAB code more efficient, it's definitely the way to go. So just as an additional cross-check on what we were doing, I've zoomed in on the steady state region at the output of the filter. So now we're looking in the time domain at the output of the filter, and what we'd like to be able to do is cross-check our earlier frequency domain analysis. So what we see coming out here in steady state, we see a single sinusoid riding on a DC value of 10, which is what our earlier analysis said. What about the peak-to-peak value of this sinusoid? We don't have samples everywhere, so we have to imagine that there's actually sample values filling in here if we had the full density of samples that we could get with an effective higher sampling rate. But if we just sort of fudge that number in approximately and say, what is this value as measured in MATLAB? It's 3.3138 approximately, and half of that is 1.6568. So if we were to go back up here to the earlier example, where we did that at the signal that survived the filter had a gain of 0.4142, and it was multiplied times the input amplitude of 4. That gave us a peak value of 1.6569. So that agrees, right? So we can see from our frequency domain analysis using the frequency response that the peak value of the sinusoid is that. If we were to examine more closely, we could observe that the sinusoid's been phase shifted to minus pi over 8, and that's a little bit trickier to find. In the time domain, we have to do that based on a zero crossing. So to see the fact that it's lagged, I have to look at a zero crossing. And here I just explained how that the lag of the peak relative to zero occurs at sample, I guess it is 8.5. So it's 8.5 samples, and we have to know how many samples per period. and then we can come up with an equivalent phase because we know that relationship between time delay and phase shift. So that also holds true. Okay, things that we're going to be spending more time on are properties of the frequency response. I have to stop and pause here, and we have to negotiate on the homework. I've got just 3 problems on here. I mean, I'm willing to let you have till Monday. It's just we're going to, I don't know, keeping the pedal down, make sure we don't have as much cramming and ramming and jamming at the end of the semester is what it comes down to. I'm looking at what we have in here. We have problems very similar to what we've already talked about. A slightly more exotic problem is this number 3. But I say slightly more exotic if you have to get the difference equation. I guess that's something we haven't gone through. It's in the notes, though. It's right. It's this topic right here. And we're out of time right now. Do you want to, if I ask you, you'll probably say no, but I'll just ask anyway and see what the reaction is. How many are interested in turning the homework in on Friday just to get it done to move on? It just requires reading a little bit more on the notes to learn how to relate a difference equation to the frequency response. It's all in this example right here and a couple other examples. In this chapter, we're going to move on to the Z-transform after we look at these properties. There's not an intense amount, but I know you have a lab due on Friday, right? Which I understand some people are definitely still working on. Okay, what's the vote? Okay. My wife was telling me, or somebody was telling me, it's part of our human nature to procrastinate. Is that true, do you think? Because I do it. Everybody, I think she said everybody procrastinates in one form or another. Okay. I'll put that up on the website, and it's now in the video. You still will have a quiz, though.